Section 2.7, Linear Inequalities and Absolute Value Inequalities. Throughout this section, we're going to solve several types of inequalities, both linear and inequalities involving absolute values. One thing we have to be aware of when we solve inequalities is that typically there's infinitely many solutions to an inequality. So we're going to come up with notation to help us represent all the solutions in a nice condensed way. The notation we're going to focus on the most is what we're going to call interval notation. Below is a table of several different scenarios of what we can see when we solve inequalities. We may have that our solutions are between two values, as we see with these four items here, or we may have that x is larger than some number, but x can be as large as we want it to be, or we may have x being smaller than some number, but x can be as small as it wants to be. It can turn out that every number is a solution, or we may have that our solution is less than a number but greater than another number. To help condense all of this writing with the inequalities, the interval notation is used to help us represent what our solutions are in between. If our solution does not have a lower bound, meaning our solution can be as small as it wants, notice how we use the symbol negative infinity. On the other hand, if our solution can be any large number as large as it wants to be, on the other hand, if our solution has no upper bound, meaning it's as large as we want it to be, we use the symbol positive infinity. A couple of things to note about the choice between parentheses or brackets. The parentheses are used to indicate that the number itself is not part of the interval. So if you look at all of the inequalities where x is either strictly greater or strictly less than a value, notice how we have a parenthesis around that number. Also, because infinity can never be contained, we also have parentheses by default around positive infinity or negative infinity. And lastly, we use square braces to indicate that the number is included in the interval. So if we take a look at inequalities like x is greater than or equal to a or x is less than or equal to b, notice how we have a square bracket around the a and b respectively because they are solutions to that inequality. Next, we're going to translate each phrase into an inequality, then into an interval, and then graph. First, all real numbers greater than -3. Here, we're going to let our variable be x, and we know we're comparing to -3. But what would be the inequality sign between x and -3? Well, we're told we're looking at all real numbers greater than x. Well, that means our real number x should be strictly larger than -3. So we have x is greater than -3 is the inequality that will represent this phrase. Now we'll write the interval notation. We know our interval notation should involve -3 by looking at the inequality, and we also see that x has no upper bound. It can be as large as it wants to be. So our interval is going to involve infinity. Now, what do we put around the -3 or infinity? So what do we put around the -3 and the infinity? Well, infinity by default always gets a parenthesis. Now here, since our real number x cannot be -3 because it's strictly larger than -3, -3 must be excluded. So we're going to put a parenthesis around -3. Next, we're going to graph. Now we know -3 is used to help represent my inequality and interval. So we're going to plot a point at -3. Since -3 is not part of our interval, we're going to graph with an open circle over -3. We use open circles to represent values that are not part of our inequality, but are used to describe our inequality. Since we know x is larger than -3 and values to the right of -3 are larger than -3, we're going to shade the part of the number line to the right of -3. And there's our graph. Next, we're going to write all real numbers between -2 and 5, including -2. So just like before, we're going to let x be our real number, and we know that's going to be between -2 and +5. Now we're told we're including -2. For our inequality sign, we're going to put the less than or equal to, because we know since x has to be between -2 and 5, x has to be bigger than -2, but because of the word including, x can be -2. As far as between the x and the 5, we're not told we're including 5. But since x is between -2 and 5, x does have to be smaller than 5. But no, equals 2 because we're not saying we're including 5. Now, what would be our interval? Well, the two numbers involved, we see are -2 and 5 since x has to be between them. But what do we put around the -2 and the 5? Well, since x can be equal to -2, we put a square bracket around -2. But x cannot be 5, so we put a parenthesis around 5. Now for the graph, we're going to plot points over -2 and 5. Since x can be -2, we use the fill-in dot that we're going to call a closed circle. Now 5, since x cannot be 5, we're going to use the open circle like we did in the previous problem. And since x is between -2 and 5, we're going to shade part of the number line that's between -2 and 5. Lastly, we're going to represent the set of all x such that x is less than or equal to -1 or x is greater than 3, which here is in set builder notation. The benefit of set builder notation versus just phrasing is we already know what inequalities are involved. So we can jump straight into making the intervals. For x less than or equal to -1, x can be as small as it wants to be, so we'll have a negative infinity. And by default, infinities get a parenthesis. The largest x can be as -1, and x can be -1, so we put a square bracket around -1. As for the x is greater than 3, the smallest x can be is 3, but 3 gets a parenthesis because x can't actually be 3, it can just be really, really, really close to 3. X can be as large as it wants to be, so we'll put an infinity, and infinities always get a parenthesis. The last part we need to translate is the word or. Or is going to be represented by this U shape that is called the union sign. So our interval is -infinity to -1 with a bracket around -1, union 3 to infinity. Now we'll graph each interval. For the first interval, the -infinity to -1, we'll put a closed dot on -1. And since we're dealing with values smaller than -1, we're going to shade to the left of -1. As for the 3 to infinity, we'll put an open circle over 3, and we're going to shade to the right of 3 since we're dealing with values bigger than 3. And there's the graph of the set builder notation and our intervals. What are inequalities? Inequalities look like equations. The biggest difference is they use inequality signs, such as the less than, greater than or equal to, or less than or equal to signs, as opposed to the equal sign we see in equations. We're going to start off by learning how to solve linear inequalities. Linear inequalities are the most basic form of inequalities we can solve. What's great about solving linear inequalities is that it's almost exactly the same as solving a linear equation. The only difference is that if you multiply or divide the same side of your inequality by a negative number, you must remember to flip the inequality. Why is this important? We all agree that 5 is less than 6. Let's say I multiply both sides of my inequality by negative 1. Well, then we get negative 5 on the left-hand side, negative 6 on the right-hand side. What happens if I forget to flip the inequality sign? Well, I would say negative 5 is less than negative 6, but that's clearly false. But negative 5 we know is greater than negative 6, so this would be correct. But the only way this would be correct is if we remember to flip the inequality sign. Remember, whenever you multiply or divide by a negative number, you must flip the inequality sign. Any other time, the inequality sign will stay the same. Now we're going to solve each of the following inequalities. We'll start off with 3x plus 4 is less than or equal to 7. And just like what we stated on the previous slide, we're going to solve this linear inequality just like an equation, but we just have to be careful when we multiply or divide. We'll start by subtracting 4 from each side, and we're left with 3x is less than or equal to 3. Next, we'll divide each side by 3. Since 3 is a positive number, the inequality sign will stay the same. And after we simplify, we get x is less than or equal to 1. From this, we can write our answer in interval notation. We're dealing with values smaller than 1, so our interval is going to involve negative infinity and 1. And remember, negative infinity always gets a parenthesis. Since x can equal 1, we'll put a square bracket around 1. And this interval will represent the solution to our inequality. Next, we're going to solve negative w over 4 plus 2/3 is greater than 5/12. Well, if this was an equation, the strategy we would use to solve it is clearing denominators. We're still going to use that strategy here, even though we're working with an inequality. The LCD of our denominators is 12, so we'll multiply both sides of our equation by 12. Since 12 is positive, our inequality sign remains the same. On the left-hand side, we'll get 5. On the right-hand side, when we distribute into 12 and simplify, we get negative 3w plus 8. Now we'll continue solving, subtract 8 from both sides, and we get negative 3w is greater than negative 3. Then we'll divide both sides by negative 3. Since we're dividing by a negative number, we must flip the inequality sign. On the left-hand side, we are left with w. On the right-hand side, we're left with 1. So we get w is less than 1, and we can write our solution as the interval negative infinity to 1 with parentheses around both negative infinity and 1. Next, we're going to solve this inequality here. Negative the quantity negative 2 plus 3z is greater than or equal to negative 1 minus 2z. Well, just like with equations, we do want to simplify each side of the inequality. I'll start off by distributing in negative 1. And we get 2 minus 3z is greater than or equal to negative 1 minus 2z. Now, just like with equations, I do want to get all my z terms on one side of the equation. So I'll add 2z to both sides. And I also want to get my non-z terms to the other side. So we'll subtract 2 at the same time. After we simplify by collecting like terms, we get negative z is greater than or equal to negative 3. Then we'll divide both sides by negative 1. And because we're dividing by a negative number, the inequality sign must flip. And we get z is less than or equal to 3. As an interval, this would be the interval from negative infinity to 3 with a square bracket around 3. Now we're going to solve 4 times 5 minus 2t plus 4 less than negative 2t plus 3. Just like in the last problem, we're going to start by simplifying the left-hand side. We'll first distribute in the 4. Then we'll combine like terms. Now that the left-hand side is simplified, we'll get all of our t terms to the left by adding 2t to both sides. We'll get our non-t terms to the right by subtracting 24. And if we simplify, we get negative 6t is less than negative 21. Then we'll divide both sides by negative 6. Since we're dividing by a negative number, the inequality sign flips. And when we reduce our fraction, we get t is greater than 7/2. As an interval, this would be the interval 7/2 to infinity with a parenthesis around the 7/2. Next, we'll talk about compound inequalities. A compound inequality includes 2 or more inequalities in one statement combined with the words and or. It's very important we pay attention to whether the compound inequalities are brought together with or the word and. A solution to an or compound inequality must be a solution to at least one of the inequalities. It doesn't necessarily have to be a solution to all of the inequalities. So long as it's a solution to at least one of them, it is a solution to the compound inequality. On the other hand, if the word linking our inequalities is and, then the solution to the compound inequality must be a solution to all of the inequalities. If we're talking about how to visualize them on a graph, for the or inequality, if the number is shaded in some fashion on the graph, it's part of the solution to the compound inequality. On the other hand, the solution to the and compound inequalities must be shaded by all of the graphs from each individual inequality. Now let's solve a few compound inequalities. Our first compound inequality is 2x plus 3 less than negative 5, or x plus 5 is greater than 4. The first step of solving a compound inequality is to first solve each individual inequality. We'll start by solving the 2x plus 3 is less than -5, and the way we'll solve this is by subtracting 3 from both sides and then dividing both sides by 2, and we get x is less than -4. In the next compound inequality, now we'll solve the next inequality, the x plus 5 is greater than 4, and when we subtract 5 from both sides, we get x is greater than -1. Now, to see what our solution will be for the compound inequality, let's graph each inequality solution one at a time. We'll graph the x is less than -4 in red, and we'll graph the x is greater than -1 in blue, and lastly, we'll turn to our keyword linking the compound inequality. Our keyword here is the word or. So our solution to the compound inequality linked together by or are going to be numbers that are solutions to at least one of the two inequalities. Well, taking a look at our graph, anything in blue is a solution to the second inequality, while anything in red is a solution to the first inequality. So highlighting both of those in orange, that would represent the solution to our compound inequality. As far as interval notation goes, the left part of our solution would be represented by -infinity to -4. The right part would be -1 to infinity. Remember, we're putting parentheses around the -4 and -1 because they are not solutions to either inequality, and then the union sign in the middle. And there's our solution to the compound inequality. Next, we'll solve the compound inequality 3x plus 3 is less than or equal to 3, and x plus 5 is greater than 2. We'll start by solving the first inequality, and after solving by subtracting 3 and dividing by 3, we get x is less than or equal to 0. Now we'll solve the second inequality. By subtracting 5 from both sides, we get x is greater than -3. We'll plot the solution to the first inequality in red, then the solution to the second inequality in blue. Now the key word for the compound inequality is and. To be a solution to the and compound inequality, we must be a solution to both of the inequalities. If we take a look at our graph, this is going to be where our red and blue overlap. Well, we can see they overlap between -3 and 0, which I'm highlighting in orange. At the point 0, because of the closed dot, it is a solution to the first and second inequality. So we'll highlight that in orange. However, the -3 is only a solution to the first inequality. It is not a solution to the second inequality because of the open dot. So we'll put an open dot there in orange. Now, orange would represent the graph of our solutions to the compound inequality, which would be the interval -3 to 0, with a parenthesis around the -3 and a square bracket around 0. Now we're going to solve 3 plus x is greater than 7x minus 2, which is greater than or equal to 5x minus 10. When solving this kind of compound inequality, we're going to actually split it up into two. Our first inequality is 3 plus x is greater than 7x minus 2, and our second inequality is 7x minus 2 is greater than or equal to 5x minus 10. Now the word joining these compound inequalities is the word and, because in order for the above inequality to work out, we have that 3 plus x must be greater than 7x minus 2, and at the same time, 7x minus 2 has to be greater than or equal to 5x minus 10. Now we can go ahead and solve each inequality. When we solve the first inequality, we get x is less than 5/6. When we solve the second, we have x is greater than or equal to -4. Now we'll graph both inequalities on the number line, starting with the x is less than 5/6 in dark orange, then the x is greater than or equal to -4 in blue. Now that we have both solutions graphed, recall our word linking our compound inequality was and means we're looking for where the graphs overlap, which we can see they start here at -4 and they end at 5/6. So from the graph, the solution of our compound inequality is -4 to 5/6, bracket around the -4, parenthesis around the 5/6. Next, we're going to solve the following compound inequality, 3 less than 2x plus 3 less than or equal to 7. We could split this inequality up into two smaller inequalities like we saw in the previous example. However, what makes this particular compound inequality different than the last example is how the outside expressions of this inequality are constant numbers, not expressions like in the last example. So if we were to separate them, we would solve both of those resulting inequalities the exact same way. Subtract 3, divide by 2. Well, instead of splitting it up, we're going to subtract 3 from each expression. And when we do, we get 0 is less than 2x less than or equal to 4. And then to finish solving, we'll divide each expression by 2. And because 2 is positive, neither of the inequalities flip. So we get that 0 is less than x, less than or equal to 4, which we can translate easily into the interval 0 to 4, where we have parentheses around the 0, bracket around the 4. If the outer ends of this compound inequality had the variable, we would have to split like what we did in the previous example. But here, since they're constants, we did not have to split up in two parts, and we were able to solve quite quickly. Now we're going to solve inequalities involving absolute values. Just like with equations, we do have to think about how do we get rid of the absolute values. Recall that the absolute value of an expression represents how far that expression is from 0. So here, if u is an algebraic expression and d is a positive real number, if u is less than d, that means u is within d units of 0. If we were to sketch a number line, we'll put 0 at the center. We know there's only two numbers that are d units away from 0. That is -d and +d. Well, if the absolute value of u is less than d, that means I have to be within d units of 0, which means I would have to be between -d and d. But I cannot be -d and d because I'm within d units. So the way we would drop the absolute values is we would make a compound inequality, -d is less than u, which is less than d. If we have the less than or equal to, well, I'm still between -d and d like before, but now I can be -d or d because I can be exactly d units away from 0. So we would have the less than or equal to instead of just the less than. Now let's say the absolute value of u is greater than d. That means my expression is more than d units away from 0. Well, there's two ways I can be more than d units away from 0. Either I can be to the left of 0, more than d units, which means my expression u would have to be less than -d, or I can be more than d units to the right of 0, meaning u would have to be greater than d. And because the absolute value of u is strictly greater than d, I cannot be exactly d units away from 0, so u cannot be d or -d. On the other hand, if the absolute value of u is greater than or equal to d, well, now I can be equal to d or negative d. So my compound inequality becomes u is less than or equal to negative d, or u is greater than or equal to d. And that is how we're going to handle the absolute values. Based off the inequality sign, we're going to rewrite our inequality as one of two compound inequalities. If we take a look at the first example, u is greater than 1. That means x is more than 1 unit away from 0. Or from our table here, we're satisfying the third case, meaning x would have to be less than negative 1, which means I'm more than 1 unit away from 0 to the left, or x would be greater than 1 because I'm more than 1 unit away on the right. And as an interval, that would be negative infinity to negative 1, union 1 to infinity with open parentheses. For the absolute value of x less than or equal to 5, well, now I'm within 5 units of 0. So x would have to be between negative 5 and 5. Since the absolute value of x can equal 5, x could be negative 5 or 5, which is precisely how we would set up in the second bullet point up here. As an interval, that'll be the interval negative 5 to 5 with closed brackets. Next, the absolute value of x is greater than or equal to 3. That means x is more than 3 units away from 0, or exactly 3 units away. Well, x could be more than 3 units from the left, which means x would have to be less than or equal to negative 3, or x could be more than 3 units away from 0 on the right, which means x would be greater than or equal to 3. As an interval, that'll be negative infinity to negative 3, square brace, union, 3 to infinity with a square brace around 3. Now, one thing we do have to be careful of is when d is negative or 0. Recall that the absolute value of u is never negative. When we're dealing with the absolute value being compared to a negative number, we have to be careful on whether or not that's always going to make sense or if it's just impossible. For our next example, we're going to take a look at the absolute value of x being greater than or equal to negative 2. Because negative 2 is negative, we're not going to split the inequality up like we did in the previous three, using the rules outlined above. Absolute value of x is always non-negative. Well, negative 2 is negative. Well, non-negative numbers are always greater than negative numbers. So this inequality is always true for whatever x you choose to plug in. So our solution as an interval would be all real numbers, which we represent with the interval negative infinity to infinity. Now we'll take a look at the absolute value of x is less than or equal to negative 3. Well, now we're asking if a non-negative number is less than or equal to a negative number. Well, this can't happen. As we stated before, non-negative numbers are always larger than negative numbers. So no matter what x I plug in, this inequality will never be satisfied, so there's no solution. Now for the next one, we have the absolute value of x is less than 0. 0 is the number that divides our positive and negative numbers. Anything bigger than 0 is positive, anything less than 0 is negative. So one way we can interpret the absolute value of x being less than 0 is they're asking, when is the absolute value negative? Well, as we discussed before, the absolute value of x can never be negative. So once again, we're left with no solution. So whenever d is positive, we can split up according to these 4 bullet points. If d is negative, we do have to be careful on whether or not the inequality will make sense or not. Same thing with d being 0, we still have to think about whether or not the inequality makes sense. Now we're going to solve each of the following inequalities that involve absolute values. For the first, we're going to solve the absolute value of 4x minus 1 less than 3. Well, the absolute value expression is already isolated, which is the first thing we want to check before we try to drop the absolute value, just like when we were trying to solve equations. Since our absolute value is already isolated, we can drop our absolute value by rewriting a compound inequality, just like what we saw in the previous slide. Since we're dealing with the less than symbol, meaning the 4x minus 1 has to be within 3 units of 0, meaning 4x minus 1 has to be between negative 3 and 3. Now we have a compound inequality similar to what we saw in example 4, where the two outer parts of the inequality are constant values, so we don't necessarily have to split it up farther into 2 inequalities linked with and. To solve, we'll just add 1 from each part, then we'll divide by 4. And we get 1/2 is less than x, which is less than 1. And to write our answer in interval notation, that's the interval negative 1/2, 1, with parentheses around the negative 1/2 and 1. In the next inequality, we're going to solve 3 times the absolute value of x minus 4 plus 2. Unlike the last example, our absolute value expression is not isolated. So that is the first thing we need to do, is get that absolute value by itself. We'll start off by subtracting 2 from both sides, then we'll divide by 3. Now that our absolute value expression is isolated, we can now drop the absolute values. Please make sure you are careful. You must isolate the absolute value before you rewrite your absolute value inequality as a compound inequality using the rules in the previous slide. Well, since the absolute value of x minus 4 is greater than or equal to 2, that means our expression x minus 2 is more than 2 units away from 0. So x minus 4 would either be less than or equal to negative 2, or x minus 4 is greater than positive 2. Now we can solve each inequality. Fortunately, we would have to add 4 to both sides of both inequalities. In the first inequality, we get x is less than or equal to 2. The second inequality, we get x is greater than or equal to 6. When we write our answer in interval notation, we get negative infinity to 2, union 6 to infinity, where we put square brackets around the 2 and the 6.